Great. So hi, everybody. It's great to see you here at the AFMS seminar for this week. So this is the second last seminar for this year. So remember to join us next week as well, and that'll be our last. It's my pleasure to introduce our seminar speaker for this week, Dr. Terry O'Kane, who is the Principal Research Scientist and the leader of the Geophysical Fluids team at CSIRO Oceans and Atmosphere. And prior to this, he's also been an ARC Future Fellow. Terry's research interests focus on non-linear and stochastic climate dynamics, and he's going to be talking about some of this work today. So please go ahead and begin, Terry.
Thanks, Kat. So look, the topic today, well, essentially is three topics that are linked. So I want to talk about stochastic and statistical dynamical models of geophysical flows. So I'm going to cover, well, it's a sort of ambitious talk in the sense that I wanted to try and link linear stochastic models to models that are non-stationary, but still linear stochastic models, and then the general underpinning or the theoretical framework that underpins all of this, and that's statistical dynamics. So you could spend a lot of time on any one of these topics, and statistical mechanics and dynamics in particular, you could spend weeks, but I'm going to try and give a broad overview of how these approaches have evolved, and also try and make some connections between the terminology that we use in atmospheric science and the terminology that's used in engineering flows, where there's essentially we often use the same tools, but we have different terminology for them. So the first part of the talk will be looking at linear stochastic models. So here you're considering, well, the question is how to quantify the variability where the time evolving or the time evolution of some variable X or state vector is represented by, what's called a generalized Langevin equation or some damped Ornstein-Uhlenbeck process. So this approach, you generally assume statistical stationarity and scale separation. So you have some slow manifold and then fast processes or processes that are a subgrid and not on the slow manifold are represented as noise, effectively closing the system. So if we just consider the simplest case, we've got a vector of fluctuations. So in atmospheric and oceanography, often we term these anomalies. So you might have some seasonal climatology, and then it's an anomaly with respect to that background state. So the state of vector evolves according to the following linear equation, where the linear deterministic dynamics are in terms of the covariance between the time lag and simultaneous covariance matrices of the state vector X. So the next part of the talk, I want to talk about non-stationary reduced order stochastic models. So where you can't assume statistical stationarity, so you've got a classically small data problem where you have multiple timescales embedded in your flow. You can no longer assume that it's statistically stationary. How do you fit some sort of reduced order stochastic model to that data set? So the approach that I'm going to describe is looking at where we approximate the dynamical processes by a vector order regressive stochastic model. So here we're moving beyond global assumptions of stationarity to assumptions that the flow is locally stationary and that the stochastic models are able to characterize the time evolution of the observations by some given model with a set of parameters, and we want to do this directly from data. And that model and its parameters are locally stationary, but globally time evolving. The stochastic model, takes a similar form where we've got our set of data instances and a mean, and then we have this matrix A, which is the set of model parameters to be determined for a given time lag up to some maximum memory depth. The E to T are again the random noise terms. Underpinning all of this is statistical dynamics, and that addresses the closure problem directly. So here we want to computationally, well, ideally computationally tractable means for the direct calculation of prognostic equations for the higher order moments. And typically we, you know, in systems that are strongly nonlinear, where there is no small parameter to do some sort of a perturbative expansion. So the expansion is in terms of the complexity of the interactions. You need to include all of the higher order moments to some approximation. And formally, this corresponds to propagator and vertex renormalization in closure. So it's a field theoretic approach. So the idea here and here is looking at all of these closures should be underpinned by a generalized Langevin equation to guarantee that they're realizable. That is, that the closures don't have negative energies. And probably the most famous closure is Craigton's direct interaction approximation. So it is underpinned by this general form of a Langevin equation, where essentially we have a nonlinear, or a deterministic nonlinear eddy damping term, and then a stochastic term that's in terms of statistically independent random variables which act on the diagonal two-time cumulant. And so in fluids, as in atmospheric dynamics, the unresolved scales are modeled according to this concept of eddy viscosity in essence. So the eddy damping term would, in its subgrid, the corresponding subgrid term would be an eddy viscosity. So the general overview of the talk is to go through reduced order models. I want to talk about some of the stochastic models of Hasselmann, given that Hasselmann shared in the 2021 Nobel Prize in Physics and effectively comes from the climate community. I'll go into the non-stationary stochastic models and optimization, have a brief look at concepts from dynamical systems to understand the deterministic dynamics in these reduced order models. And then if there's time to say a few things about statistical dynamics that, as I said, underpins most of this work. Okay, so for reduced order models, we want to do some sort of matrix factorization or some projection-based linear reduction. And in atmospheric science, empirical orthogonal functions and variants thereof, we've been using these since the late 1940s, and they were introduced by Obakov. Lorentz came along in 1956 and essentially popularized them within the weather prediction and atmospheric science community. So the EOFs are the orthogonal projection, providing linearly uncorrelated features that maximize the variance using spatial correlation structures provided by the covariance matrix. There's a very nice review of EOFs and related techniques in atmospheric science by Hanachi, Jolliffe, and Stevenson. But in engineering flows, you might more commonly refer to these as pods, so proper orthogonal decomposition. So they're equivalent to the EOFs. And they were actually introduced to the fluids community by Lumley, but again through the atmospheric community. And there's a nice review on the use of pods and also closures for reduced order models by Ahmed et al. So EOFs and pods provide an efficient way to compress the data and explain the variance of the data better than any other linear combination. And it's predicated on doing a singular value decomposition, and you're looking for the optimal low rank matrix approximation. Again, this is assuming that there is a true slow manifold exists, so there's some gap in the eigen spectrum, and then the unresolved scales can be modeled as a stochastic term. Where you have waves present, you can have degenerate eigenvalues. A way to deal with this is to generate Hilbert EOF. So it's a method for tackling propagating structures where waves in the time domain using complexified fields. Other approaches used lagged information from the time series, so lagged autocovariance matrix to find propagating or periodic signals and to deal with spatiotemporal correlations observed in the data. And these can be extended EOFs or even more popularly singular spectral analysis, which has been used for some time to for the dynamical reconstruction of low order chaotic systems. The main questions in reduced order modelling one typically asks is how many EOFs or pods are required to explain, a certain fraction of the total variance, but capture the dynamics of the slow manifold. So some work with Dylan Harries. We looked at this problem more generally as one of matrix factorization, where the problem is a dimension reduction, and we're applying this to multi-dimensional data. So given a collection of a d-dimensional data instances, we want to come up with a reduced representation in terms of a matrix whose rows are given by weights, and whose and also the columns are given in terms of the basis vectors. So the factors W and Z, so the basis vectors and weights, are calculated as the minimizers of a suitably chosen cost function, and that measures the quality of the reconstruction x hat subject to various constraints. So a typical cost function takes the form of a decomposable loss function and a set of penalty terms imposing any desired regularization. So here we're assuming that we can regularize the weights and the basis vectors independently, and a suitably chosen loss function might be the L2 norm. So within this framework of matrix factorization, you can actually consider a whole range of dimension reduction problems. So common methods of dimension reduction can now be represented within this framework. For example, principal component analysis is equivalent to simply minimizing the L2 loss function. We can also consider clustering methods. So you might consider k-means, where we're targeting features, essentially mean features in the data centroids, or at the other extreme, where we're targeting the basis, basically the data convex hull, so the extremes in the data, that would correspond to archetypal analysis. And in some sense, we can combine all this by introducing the concept of convex coding. So now we have a regularization on the weights, and by choosing or optimizing that regularization parameter, we can be anywhere between the data convex hull or the data centroids. And so this is a more general approach that now allows you to include matrix factorization within some optimization framework. Again, the thing to consider that any pre-filtering procedures are legitimate only if the features in question occur within distinct timescales that fall within some chosen frequency window. So whenever you do any kind of matrix factorization or dimension reduction, you're essentially making a choice of the spatiotemporal scales that you care about. So just to give an example of that, if we look at well, going back to Lorentz's paper from 1956. So here we're looking at an EOF decomposition of geopotential height data. So if you're not familiar what that is, effectively it's the synoptic scale variability within the troposphere. And so when you do this decomposition, you find the first mode, which is this mode here in the red, which explains the largest fraction of the total variance. It corresponds to this zonal state, these two red circles here, which are known as the southern annular mode. So this describes most of the zonal variations, although it does have a wave number 3 structure embedded within it. The eigenvalues 2 and 3 are in effect degenerate. They describe a propagating mode known as the Pacific South American mode. It has two components, one that's highly correlated with interannual tropical variability. So it has a low frequency signal embedded within this noisy structure, and a faster mode that's in quadrature with the first mode. And that's explaining, has very little interannual variability, but most of the high frequency variability. So they're so we have our first mode is a physical mode. It's observed. The second two eigenvalues comprise, if we were in Hilbert space, they would be a single wave. So they're observed physical modes. But if we go beyond that, then we start to look at this wave number 3 pattern, which is associated with the formation of coherent structures in these regions in the Tasman Sea, to the east of Cape Town, and also down around the southern tip of South America. So this wave number 3 blocking pattern, if you want to call it, actually requires the leading 8 to 10 principal components to resolve. And each of these modes has a direct correlation to surface air temperatures over Antarctica, but also in the southeastern states and in essentially the land masses of the mid-latitudes. So the EOFs are standard tools for dimension reduction in atmospheric science. They assume independence of samples and stationarity, and the higher order modes are in general not physical. They're patterns, but they require, a number of these modes. So to move from a general dimension reduction to the stochastic models of Hasselmann. So Hasselmann's famous papers are from 1976 and 1977. So this is introducing linear stochastic models to analyze climate dynamics. So the climate system has an enormous range of timescales. The central assumption of Hasselmann is that there's an existence of clear scale separation, so it's the standard assumption, allowing a coupled slow fast deterministic system controlled by a multiplicative noise correction to the average forcing. So this forms the typical null hypothesis for climate variability is a red power spectrum. So the atmospheric forcing is seen as white noise. It forces the ocean, and the ocean responds by generating low frequency variability or a red power spectrum. So Frank-Ignul and Hasselmann introduced this approach, or first applied this approach as an autoregressive AR1 linear stochastic model to investigate sea surface temperature and thermocline variability in the North Pacific. He subsequently generalized this approach to be multivariate, and I'll talk about that in quite a bit more detail coming up. But he also introduced this idea of optimal fingerprinting, and that's an approach based on stochastic models to assess whether climate models are able to faithfully reproduce the signal from natural variability. And he also introduced an approach considering Feynman diagrams for wave-wave scattering. And that has some connection to the underpinning methods that we use in statistical dynamics. And so for this work, he received a part of the 2021 Nobel Prize in Physics. So to give an overview of POPs, so this is the approach from Hasselmann's 88 paper, but I also should mention that Cecile Penland has for over many years really extended these tools and also helped to popularize them within the atmospheric and climate community. So this is a figure reproduced from a former PhD student's thesis, Jiala Liu, who's now in NOAA in Boulder. And it's just a flow chart of how you go about calculating POPs. So we have some, data. So it could be monthly data or daily data. We want to calculate an anomaly from that, or the fluctuating component. It could be detrended, it could be smooth. Then we're going to do some matrix factorization. So in this case, we'll consider an EOF analysis. And from the principal component time series, we're going to form the state vector. So from the state vector, then we calculate the dynamical operator in terms of the covariances, lagged and instantaneous. And then we do some tests to make sure that the system is stable and invertible and other properties. From here, we calculate the empirical normal modes, or the POPs, using an eigen analysis of the dynamical operator. And from there, we can calculate the eigenvalues where the real part corresponds to the damping timescales of the particular modes or pops, and then the oscillatory period from the complex part. The right and left eigenvalues can be used to calculate the pop patterns themselves. So the jth pop time series, it can be used to generate through an adjoint pattern method, the pop coefficients of the time series. Or we can consider the jth pop mode directly as some linear combination of EOF patterns weighted by the eigenvectors. So here the angle brackets denote an ensemble average or an average over time. So we're assuming that the ergodic theorem holds. Okay, so that's the general approach for calculating pops and a specific example of their application. So here we're going to generate a linear inverse model trying to understand the connection between tropical and South Pacific variability in the climate system. And so this is results from a recent paper that we published. So we take our EOF and PCA, we apply this as a pre-filter to both observed and simulated monthly sea surface temperature, and also to simulated temperatures in the subsurface ocean. So we have a global climate, coupled climate sea ice model. We can force that model at the boundary of the surface through bulk formulas generated from atmospheric observations. So from the winds, convection, etc. And from that we can generate through the ocean response quite good correspondence between the ocean surface variability and what's observed directly through satellite observations. So here we're going to look at two domains. One of the domains is the tropical Pacific between 20 south and 20 north, and restricted to 120 east to 60 west, and also then the South Pacific subtropics or mid-latitudes between 70 south to 22.5 degrees south, and again for the same latitudinal domain. So here the state vector is essentially these stacked principal components, and as I said, the conjugate complex eigenvalues and eigenvectors allow us to identify damping timescales and oscillatory periods. So the different dynamical processes are then represented by each of the distinct damping timescales via the decomposition of the linear inverse model. And so in the course of a number of papers in investigation, we were able to identify a schematic or a paradigmatic model of South Pacific Ocean variability and predictability, and also identify an oceanic bridge between the dynamics of the mid-latitude South Pacific and tropical variability associated with the El Nino Southern Oscillation, which is the leading mode of interannual variability in the tropical Pacific. And that's connected to this mode, which is called the South Pacific Decadal Oscillation, which is the low frequency variability in the South Pacific. So the ocean is responding to the atmospheric driver, and we can also use the approach to identify the relevant dynamical mode within the atmosphere that's generating this variability or low frequency signal in the ocean, and that turns out to be these two components of the Pacific South American mode. One correlated strongly to interannual variability in the tropical Pacific, and the other this faster mode. So it turns out that the faster mode, the PSA2, which is essentially representative of synoptic scale variability in extending from southeastern Australia across the South Pacific and into the South Atlantic. It turns out to be able to be the prime generator of an optimal precursor So this is the optimal initial pattern that after 9 months evolves to generate the South Pacific decadal oscillation pattern. And then in turn, drives this variability in the subsurface ocean. And as I said, that mode then has a connection to the tropical Pacific, and it provides a subsurface oceanic bridge between the variability of the tropical Pacific and El Nino and ENSO and the dynamics of the South Pacific. Sorry. Okay, so that's fairly rapid run through of the application of statistically stationary linear inverse models. But now we're going to consider the problem where they're explicitly non-stationary, and we need to determine time-dependent model parameters to do the global optimization problem. So if we have some time series, let that be the an observed n-dimensional time series, say daily averages, we want to assume that each of the data instances can be approximated by the time discrete output of some particular direct mathematical model. So we have a model operator, a model time step, and we're going to assume some maximal lag. So the time-dependent set of model parameters are d-dimensional in the model parameter space, and we want to fit some non-stationary stochastic model of the following form. So the form of this model is that we need to determine an optimal set of freely evolving model parameters, where the first, we have a mean, again, as usual, and now we have a matrix A, which couples to the linear autoregressive factor model, which connects the observations present and past. We can also prescribe an external factor function. So this allows us to incorporate forcing terms, so external covariates. So you might want to consider, for example, the role of CO2 in driving anthropogenic change, and does CO2 drive secular behavior, and can we use this approach to identify regime transitions. So then we have another parameter, C of t, and so this is essentially a persistence parameter. So we can use this to moderate the noise, and also to select optimal frequency for the persistence of coherent features within the data set. The approach that we're going to take is more generally described in this paper by Metzner, Putzik, and Horenko. The approach is that I'm ultimately going to use is what's known as the finite element bounded variation vector autoregressive method, and this has been developed by Ilya Horenko, and it's proved to be absolutely key to being able to understand detection and attribution problems with a much more rigorous framework. So here we're going to define a global time-dependent or non-stationary model distance functional. So this describes the distance between a particular data instance and the output of our model for a fixed set of parameters. So the problem as it stands is ill-posed, and it requires some assumptions to be made about the temporal dependence of the unknown parameters theta t. So here we're going to assume that at any time t, the model can be approximated by one of k local time independent model distance functionals, and they're chosen according to some time dependent set of probabilities. So effectively we're assuming that it's locally stationary, and we want to determine the model affiliations in a probabilistic sense. So the probability that the data instance at any given time can be allocated to one of these K cluster states, and that's through the minimization of, it's a minimization problem. So we're going to describe the model now exactly in those terms, and the constraints are that it's a convex set of time-dependent model affiliations. Okay, so for a given number of clusters and a fixed maximal time lag, we want to minimize the distance of the model trajectory of the model metric at G at each time to one of these K clusters. And we're going to simply use the Euclidean norm to measure the model error as the squared distance between the data instance and the output of this average model functional. So we're going to do the inverse problem, or the parameter identification problem, and it's going to be approached via the solution of the following variational problem, that is the clustering of non-stationary multidimensional data in terms of the minimization of this functional. In practice, we consider all possible combinations of time lag and memory persistence. So we define an upper bound on the number of states. We can apply numerical finite elements for numerical efficiency. We're going to apply some sort of bounded variation or regularization to avoid becoming trapped in local minima. It's an annealing process, so the number of annealing steps has to be judiciously chosen. And we need to have some criteria to choose the most parsimonious model from the many models that we generate. And so in practice, you can use, or we often use information theoretic criteria such as Akai-Ika or Bayesian information criteria to select the proper order parameters of this vector order regressive model. Okay, so when you apply this to a real problem, and here we were looking at the evolution over the last six decades of the variability in the troposphere, and we wanted to and so what's occurred is that there's been a systematic shift from patterns or metastable states, dominant metastable states in the 1950s, 60s and 70s, which were in terms of positive and negative wave 3 patterns. So essentially the flow was mostly flipping between these wave 3 metastable states. And then over time, and dominated by this positive wave 3 pattern, which essentially corresponds to enhanced formation of coherent features in these major blocking regions. And so over time, this state has weakened to be going from dominant to subdominant. And then the negative wave 3 state has evolved over time to become this positive phase of the southern annular mode. So the positive phase of the now dominant zonal state, which is characterized by enhanced westerlies and a poleward shift in the westerly jet. So these averaging over all time periods gives you essentially these invariant patterns, but in reality, these patterns are evolving in time. So you could take some sliding window to see how they evolve. So we can then include the external covariates that are driving this secular behavior and these changes in the metastability of the flow, and the dominant drivers are the CO2, sulfate aerosols, say from volcanic emissions, optical thickness, so optical thickness, lagged ozone mass deficit. So we can consider seasonal effects, or considering the ozone mass deficit to be constant over the year, and then the solar constant. And so when you do all of this, and then you determine the optimal model, what we found was that the dominant driver of these changes in the dynamics of the mid-troposphere is due to the anthropogenic CO2 emissions, and then a subdominant effect is the seasonal variations in stratospheric ozone. Okay, so the next system, or the next section, is to look at using tools from dynamical systems to analyze the deterministic dynamics within these reduced order stochastic models. So we can study the dynamics of the resulting affiliation sequences and parameter matrices from this vector order regressive model to construct essentially a system of delay equations. So here we're describing a discrete linear mapping of the system that governs the deterministic reduced order model tangent dynamics with a finite number of transitions between these states. A of t again defines the linear propagator of the tangent dynamic, and from the linear propagator we can use that to construct a matrix cocycle, that is the forward and backward mapping of solutions under the tangent dynamics. And then from this we can calculate the Lyapunov exponents of the subspace, right, of each subspace. And for the asymptotic case, the space is spanned by the set of covariant Lyapunov vectors with growth rates given by the Lyapunov exponents under the tangent linear dynamics. So the variable tau represents the window over which the cocycle is defined, starting from some particular time. And the cocycle is defined as the compositions of the linear propagator in time. For finite times, for finite time Lyapunov exponents, the growth and decay rates, we can calculate an attractor dimension in terms of the Kaplan-York dimension, and we can also consider the creation of information through the Kolmogorov-Sinai entropy. And we're going to use these tools to try and understand whether the deterministic dynamics within a reduced order model calculated from this vector order regressive approach is, you know, physically realistic. And so this is work with Courtney Quinn and Dylan Harries. So here we're looking at, we're considering transitions between 3 states in the northern hemisphere troposphere, and that is the Atlantic Ridge, which is this state here, and the 2 phases of the North Atlantic Oscillation, where the North Atlantic Oscillation is typically considered or characterized by this negative phase, which is a positive height anomaly over, you know, Greenland. So the transient behavior of the leading Lyapunov vectors, or covariant Lyapunov vectors, in this case they're actually finite time mixed singular vectors. Their growth rates and finite time dimension for a representative time can be characterized in terms of, as I've said, the local attractor dimension. So the local attractor dimension is actually going to vary by not simply the value of the Lyapunov exponents, but also how these vectors align. So here, hyperbolic dynamics is characterized by the presence of expanding and contracting directions for the derivative, and it can be measured in the alignment of the dynamical by the dynamical vectors. So what we found was that we can characterize an observed time series. So here we're considering a period from, you know, over 2012 from March to August. And then we can assign each of these data instances to one of these metastable states. And then what we've noticed is that as we transition in and out of a dominant phase of the dominant negative phase of the North Atlantic Oscillation, that the transitions themselves are actually characterized by a loss of hyperbolicity and alignment between the leading 3 Lyapunov exponents. And that corresponds to dramatic changes in the dimension of this local attractor. And so fundamentally what we found, as you transition from, you know, one state to another, if we consider all transitions, that the transitions themselves are characterized by first an alignment between the leading and second Lyapunov vector then between the second and third, and then a alignment between the first and the third. So what's happening here is that we have the dimensionality is typically dominated by the leading exponent, but during transitions, the near neutral or weakly stable exponent that has the longest time scale in the system, it can fluctuate to become locally positive, and it's corresponding to a reduction in the strength of the leading unstable exponent, and an increase in the stability of the most stable exponent. So there's a complex interplay of dynamics embedded within this highly reduced order deterministic part of this stochastic model that's very accurately capturing the local dynamics of this observed time series. So just as a final aside, I thought I'd mention some, well, essentially the work that underpins all of this. So in recent years, there's been significant progress in the development and application of dynamical subgrid scale parameterizations for geophysical flows based on statistical, dynamical, and stochastic methods. So in statistical dynamics, the subgrid model itself is determined self-consistently from the higher resolution closure calculations, or it could be done from direct numerical simulations. So statistical dynamical closure theory is a natural framework for the systematic approach to subgrid modeling for geophysical flows, since it's generally only possible to represent the statistical effects of the unresolved eddies, while their phase relationships will be with the resolved scales that are typically lost with a stochastic model. But the closure theories are complex. So they're based on renormalized perturbation theory and path integral methodologies. And fundamentally, you have to have an exact generalized Langevin model representation that's going to allow for the, for the system to be realizable. So maybe I've got a few more minutes and I can go through this in a little bit more detail. So if we consider the simplest system, so a quadratic nonlinearity such as the Navier-Stokes equations for homogeneous isotropic turbulence. So we can describe the statistical behavior of a turbulent flow in this term. So we consider a generic equation of motion with a quadratic nonlinearity, with no mean field and the fluctuating part of the vorticity. So in Fourier space, we can write that in the following form, where we have a random forcing term F, or a stirring force, with a random Gaussian, well, with a Gaussian distribution. And then we can do a perturbative expansion. The difficulty is that this expansion parameter is close to 1 or larger. And so there is no small parameter with which to do this expansion. And so the expansion is necessarily in terms of the complexity of the interactions. From this, we can define an inverse operator, and this is given in terms of the bare or viscous response function. That's a Green's function. It describes the response of the system, or the instantaneous response of the system to small perturbations at 2 wave numbers. And then we can write this expansion now for the 0th, 1st, 2nd, and higher order terms. And then we can write the diagonal cumulants in terms of combinations of 0th and higher order expansive terms. So we're substituting for the coefficients and factorizing the moments using the standard rules of Gaussian statistics. And this is what essentially is the approach taken by Creighton and others. At this point, you've got to make some assumptions. So the closure expressions, so that expansion turns out to have singularities, and they have to be dealt with. So that requires the application of renormalization and regularization methods. So that's the introduction of a response function where we have these 2 observables. we need to have an exact underpinning generalized Langevin equation. And if we include waves, so a mean field and say a topography that generates a mean field, so an inhomogeneous non-Markovian problem, that will in itself introduce an additional propagator which contains these mean field and topographic terms. So third order corresponds to non-Gaussian statistics, and to deal with the inhomogeneous problem, which is essentially how do you make tractable the covariances in the approach here, which is that we're using, and so this is ideas originally generated by Creighton, but then Jorgen Fredrickson used these ideas to generate really the breakthrough idea, and which is this quasi-diagonal direct interaction approximation. And he applied that to generate subgrid scale parameterizations of the eddy topographic force, eddy viscosity, and stochastic backscatter for flow over topography. So here we're going to assume that the statistics are initially multivariate Gaussian, although we can implement other methodologies to go beyond that, and then to zeroth order that it's diagonally dominant. We want to guarantee random Galilean invariance, so that the signal time correlations of any order, both random or deterministic, should be invariant under Galilean transformation. And we need to make a choice of the underlying fluctuation dissipation theorem. So, and then we need to extend to include differential rotation and memory effects. So this can all be done diagrammatically. So the expansion up to second order in terms of the homogeneous components. The essential takeaway point here is that from a field theoretic point of view, you're actually looking for closed loop expressions. And this turns out to be very powerful. So this is an expansion to second order, where the vertex terms are essentially the interaction coefficients between these triads in wave number space, and the propagators are the cumulants and response functions, and these terms have singularities, and the way to get around that is to renormalize them. So replace the zeroth order terms by their exact representation. If we include, more complicated flows with, large-scale east-west flow, topographic effects, differential rotation that are generating Rossby waves, it becomes more complicated, or dramatically more complicated, but the take-home point is that this can all be done in a consistent manner where you now define this additional propagator, which includes these mean field topographic effects, and again, you're looking for these closed-loop representations. And so, underpinning all of that is a more generalized Langevin equation, which now includes these pi terms. It's the same as the one that underpins the original direct interaction approximation of Creighton, but now it includes additional terms that are incorporating the generation of the mean field due to topographic effects. And so this can all be applied then to look at flow over topography, and so these integral terms can be the homogeneous. Some of them they're complex because we've got the presence of waves. They're anisotropic for any terms that involve the mean field and the topography, but fundamentally you can pull out the subgrid terms, and so the subgrid terms tend to be representative of high-pass filters of the Rossby waves, or these eddy topographic effects, which are high-pass filters of the topography. So I think I will just point out that if anyone is really taken by the closure theory and you want a much more detailed explanation, you can look at our paper in Journal of Fluid Mechanics, which is looking at Markovian inhomogeneous closures. So removing the need for these long time history integrals. And also I have a talk on YouTube which goes through that in quite a bit of detail. So thank you.
Fantastic. Thank you for that talk. You covered so many different models. It was fantastic. We do have time for questions. So if you do have a question, feel free to just unmute and ask, or you put your hand up in the participants list, or just even dive into the chat. I'm not sure if you can see the chat, Terry, but Vasily did put a question in. I'll just read it out for the recording. Yep. So Vasily was asking, given the quasi-diagonal direct interaction approximation, QDIA, assumes that the subgrid tendency for a given spatial scale is dominantly dependent upon the flow field of that same scale as opposed to other scales. The turbulence closures you presented are ideally suited for flow configurations that can be simulated spectrally. Do you see a way forward for flows of more complex geometries that cannot be simulated spectrally in one or more dimensions, for example, spectral element methods, or could one adopt a basis of POD, EOF, or some other set of global modes that could be defined on an irregular grid?
Yeah, so that's a big question.
Long one. I wasn't sure I was getting into. That's fantastic. Yep.
Yeah, thanks, Vasily. Yeah, so look, actually, Jorgen Fredriksson and I were talking about this today. So one approach that you could do is you could go to spherical geometries. And that gets somewhat the equations. Well, if I lay out the equations, they're already very complicated. They become more complicated, but that could be done. Yeah, going to complex engineering type geometries is always going to be difficult because this approach is most elegant, I suppose is the best way to put it, in Fourier space. That said, it has it has direct applications to general problems in quantum field theory, particularly for semi-classical approximations to general field theoretic approaches. But yeah, look, it is a significant challenge. You could go to spectral elements, but yeah, yeah, complex geometries will always be difficult. I can't see a clear way forward.
Thank you for the answer. I can forward this to Vasily so I can have a look later. All right, any other questions coming from the audience? Just while people are kind of having a bit of, oh, here we go. Richard has his hand up. Go ahead.
Yes, thank you, Terry. A big question, but a very difficult question, I suppose, is whether the period of something like the El Niño Southern Oscillation has been shifting over recent decades. It's, I guess, a very challenging and difficult question to try to address because we've only got a few periods.
Yep.
And if one tries to go back further in the past, the data is changing in quality and becoming much more sparse in quality. Is there any hope these methods could be applicable over long time scales?
Yeah, so in actual fact, I have applied the non-stationary VAR-X optimization approach of ILIA to El Niño, and you can pull out the phases of El Niño as the metastable states, and then you can also look at exactly the question that you asked, like the changing frequency and persistence of, say, El Niño, La Niña, and the various flavors of it. So whether it's a Central Pacific El Niño or an Eastern Pacific El Niño, and we can actually then apply Markovianized variants of this to generate predictive models, which are akin to the early days of weather prediction, where you're looking for, in effect, the optimal or set of optimal precursors for particular flavors of El Niño. So yeah, so there's you know, there's huge potential for that particular method to be applied to that problem. And also it's got the things that, even though you know, we don't have a sufficiently long record for it to be statistically stationary, there is a clear slow manifold, and so it's, you know, it's the perfect problem for some of these non-stationary optimization tools.
So are you in a position yet to make a call on whether it's changing?
So yeah, so there's clearly in the work that we've been doing, there's clearly a correlation between the flavor of El Nino and, say, the background state, which would be, you know, the IPO, so the interdecadal Pacific oscillation. So there's a clear correlation between the prevalence of a particular class of, say, Eastern Pacific central and frequency of Central Pacific El Ninos, according to what phase of the IPO you're in. But that's given that our observational record only has 2 phases of the IPO.
Right.
It's pretty hard to go beyond that. Yeah.
Okay.
Yeah.
Thank you.
Great, thanks, Richard. Anyone else from the audience have a question? I might just ask a quick question, which is, say for, I think, maybe like the second part of your talk, which was on the principal oscillation pattern, you gave the example of the South Pacific Ocean.
Yep.
When you apply these methods, are these like computationally expensive to apply, or are they relatively cheap? I'm just wondering, like in this day and age of where we, you know, the data is getting bigger and bigger, like how do we kind of address that? Yeah,
so the way around the, you know, so there's 2 ways to go. You can address the fact that you've got, you know, high dimensional multi-scale data, right? Which is a, you know, computationally difficult problem. So that's the reason we do the matrix factorization. So we're reducing that dimensionality down to just the basic set of modes that are able to describe the deterministic dynamics. So it's a huge reduction in dimensionality, but we're also making judicious choices of what modes of variability that we're particularly interested in. So yeah, so it's the matrix factorization is the key to making it very computationally efficient.
But yeah, the big question is, how do you choose and justify, which modes you're looking at?
Yes. Yeah, that's well, the $1 million
question. Yeah.
Well, the only caveat on the VAR-X approach is that effectively you're doing a simulated annealing problem. So you've always got that as an additional, you know, computational factor to deal with. And because you're assuming that it's locally stationary, you're doing this optimization problem for every, you know, chunk of data predicated on, you know, how big you make that local chunk of data. So that is a big computational task, and you're going to do that for every possible model. And then you're going to use your information theoretic approach to choose the, you know, the most parsimonious model from within that whole family of models. So yeah, you're back to a supercomputing problem.
Yeah, there's a lot of balance, I think, in trying to address these.
Yeah.
All right. Any other questions from the audience? Otherwise, I think we might close the seminar. All right, so thanks again, Terry, for an excellent talk. And thanks everybody for attending, and hopefully see some of you at least at our final seminar, which will be next week, next Wednesday. That'll be the final seminar of this year's AFMS series. So thank you, Terry.
Thanks.